We'll see dynamic considerations. Static analysis holds good when the loads are slowly applied. When the loads are suddenly applied or when the loads are of variable nature, the mass and acceleration effects come into picture. So if you have a solid body, such as an engineering structure, and is deformed elastically and suddenly released, it tends to vibrate about its mean position. The periodic motion due to the restoring stored energy will be called as free vibration. The number of cycles per unit time is called as frequency. Then the amplitude is the maximum displacement from the equilibrium position. Now we'll see the formulation of it. The Lagrangian is defined by L is equal to T minus phi, where T is the kinetic energy and phi is the potential energy. We have Hamilton principle, which is given as for an arbitrary time interval from T1 to T2, the state of motion of a body extremizes the functional. So, I will be equal to integration of T1 to T2 L of dt. If L can be expressed in terms of generalized variables, what are generalized variables? Q1, Q2 till Qn, Q1 dot, Q2 dot till Q1 dot, where Qi dot is dQi by dt. Then the equation of motion will be given as d by dt of dl by dqi minus dl by dqi is equal to 0. Here it is partial differentiation, where I will be from 1 to n. So they will ask you to find out the equation of motion. That time we are going to use this Hamilton's principle to find out the equation. So let us see one numerical on spring mass system. Here it says, consider the spring mass system shown in figure. Determine an expression or equation of motion using Lagrangian method. So they have given you the spring mass system. If you observe, the spring stiffnesses are K1 and K2. They are connected to masses M1 and M2. Here X1 will be the displacement due to mass 1, X2 will be the displacement due to mass 2. So you know Lagrangian is defined by T minus phi. So kinetic energy, how you find out the kinetic energy? It is half m v square, right? So m v is nothing but your velocity. So if x1 is the displacement, x1 dot will be the velocity. So at each masses you are supposed to take that, I'll be getting it as half m1 x1 dot square, that is for mass 1. Then I have half m2 x2 dot square for mass 2. This gives me the total kinetic energy for the spring mass system. So similar way, I'm supposed to find out the potential energy. So potential energy is phi is equal to, it is nothing but half kx square. So in this case, half k1 x1 square for this, the first one. If you see for the second one, it will be displaced by x2 minus x1. So this will be half k2 x2 minus x1 whole square. So now I have got the kinetic energy as well as potential energy. I can find out the Lagrangian. So Lagrangian L is equal to T minus phi. You know already P is given by half m1 x1 dot square plus half m2 x2 dot square minus, you know, the kinetic energy. Sorry, this is kinetic energy. You know the potential energy also. That is half k1 x1 square plus half k2 x2 minus x1 the whole square. Now equation of motion, you know, it is given by v by dt dl dx dot x1 dot minus dl by dx1. So if I differentiate that, I'll be getting m1 x1 double dot plus k1 x1 minus k2 x2 minus x1 is equal to 0. Similarly, if I do it for x2, so what will I get? It will be m2 x2 double dot plus k2 x2 minus x1 is equal to 0. Writing these two in matrix form, I'll be getting m1 0 0 m2 x1 double dot x2 double dot. We have taken only these two terms first. So it will be m1 0 0 m2 x1 double dot x2 double dot plus k1 plus k2 minus k2 minus k2 x1 x2 is equal to 0. I can represent it as m x double dot plus kx is equal to 0. This will be the equation of motion for a spring mass system shown.